who's here today. Thank you. Matt Newell, who's here today, will be moderating the questions off of the chat. And I think those are all the announcements usually, yes? So with that in mind, Messaoud, we're very much looking forward to your seminar.
Yeah, thank you very much, Gerald. Thanks a lot for organizing this journal, and it's my pleasure really to introduce to the XAFS community one of the latest XAFS beamlines that is constructed in the Middle East, and it's the only one really in the Middle East. So I joined SESAME in 2011, starting working on this beamline. So I will introduce it to the users, and let's hope that this will work there. Okay, yeah. So in this presentation, I will more focus on technical part. Maybe I start with an overview of the SESAME, which stands for synchrotron light for experimental science and applications in the Middle East. I'll go through quickly for the evolution and the brief history of SESAME, which is really a good story. Then some parameters of the machine and the beamlines that we have currently now. Then I will explain about or say more about the beamline itself, which is called XAFS XRF. In reality, it's more XAFS than XRF. And at the end, after a short pause for questions, we can go for selected case studies, which are collaborations with the beamline scientists from the region. And these are experiments that were scientific applications that were done at our beamline. If we have time, we can go over 3 of them. If not, we just stick on 1 or 2 examples. So among all these red points that we see on the world that really represent the top number of synchrotron facilities around the world, one blinking there is what we call now SESAME. It doesn't look like a synchrotron from outside, but anyway, I swear that it's a synchrotron. You will see inside in a few minutes. So the SESAME starts as an idea in the 80s by the Nobel laureate Abdus Salam from Pakistan, where he wanted to have a synchrotron in the Middle East. Then in the 90s, people really started thinking that, yeah, for sure, we need something that is similar to CERN, where we can create cooperations between countries in conflict in the Middle East. You know, Middle East is known for now decades and centuries that it's not stable region where we have a lot of conflicts. Then SESAME was really one of the science for peace that really wanted to prevent such conflict. Then late 90s, Gosvos and Herman Vinek proposed to reuse the BC1 synchrotron after a technical advisory committee meeting that was in Germany for the upgrade of BC1. And there was a question, what will become BC1? And here comes the idea that, yeah, of course, we can think about a place in the Middle East where we can reuse these components from BC1, and the name SESAME. I think all of you knows what SESAME, open SESAME. So that's what they wanted to have. It is like SESAME will open the peaceful or the peace for the region. Then in the late 90s, they started a interim council, where they started really making workshops. They were organizing schools, looking for trainings for people from the region. And then in 2002, they decided to go from second generation, which was BC1 synchrotron, to a third generation facility, 2.5 giga-electron volt. And that was decided in 2003. Then there was a while where there was nothing happening, because it was the period where they were building the community and having trainings. In 2008, they started installing the first component or the first accelerator from BC1, which was a microtron. So you just guessed that we don't use a LINAC, but we use a microtron, a circular accelerator. Then in 2009, we had the first beam. In 2011, I joined the SESAME, and we got the full beam from the microtron. In 2014, we started commissioning the booster. And in 2016, we started commissioning the storage ring after the installation. In 2017, we had a full or the operation of the first beamline in the Middle East. I was really a lucky guy who was operating this first beamline. Then in 2018, the IR beamline joined, and we were 2 in 2018. The count or the members of SESAME are in the Middle East, but not all the Middle East countries are part of SESAME. But we can see some are not from the Middle East, but they are considered of Middle East, like Pakistan, Iran, Turkey, Cyprus, Egypt, Jordan, Israel, Palestine. And then we have also observers that they help into constructing the SESAME. Also, they help in the discussion and training the people from SESAME or the staff. So this is how it looks like from inside. So forgetting about the building, I removed the roof. And inside you see a microtron that accelerates the electrons into 22 mega electron volts. Then we have a booster. It's not a full booster, full injection booster. It's just 0.8 giga electron volt. That means we cannot we use also the storage ring as an accelerator to get to 2.5 giga electron volt. This means also that we cannot use a top-up mode, and up to now we are working with the decay mode. So we inject once per day, and it lasts to the second day while the beam is decaying. So this is another image of the synchrotron showing where the beam lines are, and these are most of the X-ray beam lines, and the IR beam line is from the other side. So the storage ring can get up to 22 beam line. So as I mentioned, it's a 2.5 giga electron volt for a circumference of 133 meters about. The current, it was designed for 400 milliamps, but currently we are working with 250, and there is a possibility to go to 300 milliamps with a lifetime that goes more than, we are injecting for 24 hours. And when we see, this is something that we compare the flux with old synchrotrons, like they're quite old now. When we talk about the SLS, they are going to upgrade. Soleil also are going to upgrade. ESRF already upgrade, and so we were comparable to the other facilities. So it is good that they thought about upgrading to 2.5 giga electron volt. So this is what we have done up to now 2009. They worked only on the microtron. It was completely refurbished by the SESAME employees. And in 2011, we got the full beam. In 2014, there was a beam. In 2017, this is just one beam line. What you can see here is just the XAFS XRF beam line that was under commissioning. And then in 2018, we were just 2 beam lines. Nowadays, this is the current status where we have, where we inject to 250 milliamps, and then we have 5 operational beam lines, fully operational. In the future, we will have another beam line here, or it's a branch of the beam line for soft X-rays, which is called the TXPS, for mainly for soft X-rays. One good point that SESAME really it's really a good point for SESAME, that it's a green facility. And thanks to the European Union for funding about $7.2 million US. SESAME is now totally powered by through the solar power plants. So that was about SESAME. I think I was very brief and quick. Now I move to the beamline. And the XAFS beamline, first, so you see this logo up there. It's the Robel beamline, or the Helmholtz Zentrum Dresden Rosendorf. So a great thank to Andreas Scheinost, who is the beamline scientist or the beamline manager of the Robel beamline at the SRF, where they upgraded in 2000. They upgraded their beamline. So at that time, I was at the SLS, or the beamline scientist at the Superclass beamline. I met with Andreas Scheinost, and he mentioned that they are going to make an upgrade of their beamline for about 6 million. So I asked for this, the components, and it appeared that they can donate them to SESAME, which they did, thankfully. And we moved them from ESRF to SESAME in 2012, and we installed them as you see them in here. So then you know that the SRF is really having higher power and higher flux also. Therefore, we had to adapt these components to our beamline. Since going from higher to lower is not a problem, it was very easy to adapt them to SESAME, and using an horizontal acceptance of 3.2 milliradians and the vertical 0.3 milliradians, we can cover an energy range of 4.7 to 30 kiloelectron volts. I just have to mention that XAFS beamline is a bending magnet. It was the first beamline, so it has to be easy to operate. So we decided to go for a bending magnet beamline. But I mean, we can get for a photon flux that is up to 10 to the 12 photon per second at 8 kiloelectron volts. So up to now, and due to a lack in the financial support or and the budget, we are not able to do many things. I mean, we could not finish get the beamline to fully operational with the design parameters. Like we cannot focus to, we don't have a focusing system. We are thinking to use a toroidal mirror now, but yeah, we need some money. Then after that, we can use a KB mirror, and we can go down to 8 by 10 square micrometer. But this is not available nowadays, and we hope that one day we will have the money to get that. So what we have now is a 2 by 2 square millimeter that is slitted down beam. So I cannot say, you can imagine how the flux is. So the flux, how is the flux density? So there is a lot of loss in flux. The total beam can go up to 5 by 20 square millimeter. Anyway, regardless this point, we can cover all the energy range or all the elements in the periodic table except for the lower energies. So starting from titanium to the maybe up to the tin, we can do the K edges. Then with the L edges, we can do all the rest, including the actinides. Although the actinides are not, we don't have any facility or any beamline or any thing that can help in using the actinides, at the exception of natural actinides like thorium and uranium, but with a very, very low concentration, and for civil research. The optics, like all the X-ray beamlines, we have this similar optics. We have a vertical collimating mirror. Then we have a double crystal monochromator. This monochromator now is changed. It's thrown, and we are using a new. When I say new, it's dated of 2007 was constructed in 2007 by Axel. Then we have a vertical focusing mirror. The two mirrors, they have a pneumatic bender. Of course, this is an obsolete technique, but we still use them, and they are working perfectly fine. Although that we can focus in vertical, but we cannot focus in horizontal. So we are not using the vertical focusing mirror. Only we are using the vertical collimating mirror. This is how it looks like in the hatch, in the optics hatch. We have the vertical collimating mirror here. This is the new monochrome mirror built by former Axel company. And the vertical focusing mirror, which we want to change it to a toroidal mirror or a double toroidal mirror, depending on the money, if we have or not. So these are, the mirrors that we have are double coated silicon and platinum. And with platinum, we can go up to 30 kiloelectron volts. With silicon, we can cover also, we can reject the harmonics, the high harmonics, and also we can cover the L edges of the platinum. We found really a compromise between platinum and silicon for a fixed angle of 2.8 milliradians. So we don't have to move a lot with this mirror. So the motors are still fine, since they are very old. That from 1998, I think. The crystal also, we are using silicon 111 and silicon 311. So we are using the two pairs. We can change between the two crystals in just a few minutes. In the experimental station, we have a 6-axis sample manipulator. We have ionization chambers for the transmission mode. We have a single element silicon drift detector from K-Tech using the XEOL electronics. And we have the beads from INFN, just developed by INFN in collaboration with Elettra and SESAME. It's a donation from Italy to SESAME. So we decided to have something good for beamline, and this came out by the INFN Italy, to get an 8 module times 8 STDs, so it means 64 element silicon drift detector, and you can see all the elements how they look like. So this detector is operational now, and thanks to this detector, we could measure XANS of 2 ppm copper in an archaeological sample. My colleague Latifullah, who is the second beamline scientist, also is experienced with the X-ray Excited Optical Luminescence. And then now we have a spectrometer here. We can combine that with the X-rays, and you can also look at the optical luminescence of luminescent elements. So this is how the beamline looks like. And you can see the beam is coming from this part here. We have mini slits, ionization chambers. Here we can have the sample can be rotated into 45 degrees to be used for fluorescence or in transmission mode. Then we can use also the XEOL spectrometer for combined XEOL XAFS also. So I think we can stop here for some questions.
Okay, great. Thanks. That was an excellent introduction. I think currently all the questions in the chat have been answered. So if anyone has a question, please type it in the chat. I'll ask one. So I think you mentioned that the injection happens at 0.8 GeV, and then the storage ring also acts as a synchrotron to boost the energy to 2.5. How long does that take? And is there a heat load change on your... How long does it take to do the injection and getting up to 2.5 GeV? And
generally it's about half an hour to 40 minutes.
Oh, okay, okay. And then does that cause a heat load issue for your optics?
Not really. We have.
Okay.
I mean, for myself, there's no problem because I'm bending magnet, and the hit load on these components is really minor, let's say, or
Right.
minimum compared to my colleagues who are using insertion devices like the um, uh, the man, the X-ray beamline or the tomography beamline, who are using wigglers, or also the hazard beamline. Where we are using a non-dilator, yes.
Yeah. So there's also another question from Jerry asking if you thought about doing X-ray emission or crystal analyzer HRF-D work as well, or is that something that's on your wish list? Maybe
What is
we could.
the question? What is
Have you
the
thought about doing X-ray emission or HRF-D measurements with crystal analyzers?
There's the first question, I think. What is the typical spot size?
Yeah, I think you answered that, right?
Yeah, that's about
2
now we have to
millimeter.
point to the yeah, then the XES, we are thinking to do the XES, but we already proposed to the scientific advisory committee for the last meeting that we had. We proposed XES, and really they were not really that keen for that, because they said the beamline is oversubscribed. We have a factor of 3.2 oversubscription, and there is no need to go for additional techniques. But maybe in the future, if we will have another beamline, we can think about it.
Okay, great. That sounds good. I think there aren't any more questions. Why don't you continue and we can ask more questions as you go.
Okay.
Okay, great. Thanks.
Good. Yeah, let's go to now some selected case studies from that were done on this beamline, with whom we were collaborating also. Okay. I will start with this. This is an easy. That was really an easy one, but not that easy. So we start with a heavy metal exposure of 500 or 5,000 years ago. So we were looking for pigments, cosmetics, metalworks, and also human remains. Samples were collected from a region from Iran called Shahr Sukhta, and this was really a long distance trading site. It was a big market where they sell things from all the region in the Middle East, and yeah, people are exchanging their goods. And also they were some manufacturers there where they do cosmetics and jewelries and so other things. Then we wanted to know what is the effect of these heavy metals on the region itself, or also on the human remains that we have there. So we start with the human remains. We took teeth and bones. So here an example of an identical concentration of all the elements in a tooth and in the bone. And if you just overlap them, they are totally overlapping. But when we did the XAFS, they also they were looking really good. Trying to find out what is it, and the PI had this idea that they could be using some copper acetate for green pigments or fungicide, and we did a linear combination fitting using copper acetate and some other copper 2+ also, and it appeared that it's not completely copper acetate, but also it has some nucleotides and copper sulfide. Then we went to do some XAFS to see what is really the structure of the copper around the copper. Surprisingly, we had 2 types of oxygens as a coordination number at 1.74 angstroms, and that was and slightly longer one, 1.95 angstroms, and that was in 2 bones. I think we didn't do for the tooth. But anyway, so we have now to say that from the copper oxides that we have, or the oxygen number of oxygen atoms that we have, that whether we have a higher disorder, so that the atoms are completely disordered, or we have a multiphase, which could be that we have that was shown by the XANES, that we have the copper acetate and also the clinotyles and copper sulfide. But what is surprising is that there is no trace of biological elements. We don't have no carbon, no calcium, and that means that the copper here is completely diagenetic, and what we have there is something is just a contamination from the soil. So it was going to the soil. Then we went through another objects. We were just far away, a little bit far away from this market in Iran, just nearby. We had two bodies, a young female of about 20 years old and a newborn baby. So they were just lying next to each other. Here you have one and the other one. We want to see what is the effect of these two, and we did the X-ray fluorescence of the on the bones, and surprisingly we don't have much copper, but what we have is lead. Of course, we played with the energy to get to distinguish between the arsenic and lead, because they have the same the K alpha and the alpha of arsenic and lead are overlapping, completely overlapping with the detectors that we have, the energy resolution of the detectors that we have. So when we move lower to 12.5, we don't excite the lead. And what we see there is that we have only lead, and the contribution of arsenic is negligible. So this attracted us to know where the lead is coming from, because in the soil there was no lead, or the concentration of lead in the soil was really lower, much lower than the one in the bodies. Then with the XAFS, we found out that we have lead oxide, and we have lead sulfide, and the carbon. So when we look at the two first, they are really similar to the galene, as we can say in French. Galene is PBSO. And it's bind to the calcium at a slightly longer distance. When we went back to what was what type of manufacturers they had in Shahr Sukhta, it appeared that they were well known for what we call kohl. It's a kind of mascara that the women they put in their eyes to get a black eye, and big and black eye, and beautiful ladies. And that was used. They were to manufacture it. They used to manufacture it there, and this lady was the one grinding it and making it. That's why this PBSO was inhaled by this female and get into her body, and through the umbilical cord, it was transferred to the baby. And another point that really confirm this hypothesis, that the concentration of lead in the baby was higher than the one of his mother. So that confirms that this is a completely biogenetic and accumulated lead in the body. So this is the first example. If you have some questions, I think we can stop for a few questions. If not, I can go to the other example.
Are there any questions? I think maybe I don't see anything in the chat right now. So why don't you continue? We might ask more questions later.
Okay. So now we go to another example. That was one of the first experiments done at SESAME. It's about catalysis. So it's what everybody now is looking for is renewable energies. This is the group from Turkey. Turkey is a member of SESAME also. They are really contributing a lot to SESAME, and they are very active, and they have a large community using at least on my beamline, on the XAFS beamline. And they are not only using the SESAME facilities, but also worldwide facilities. And this is the group of Emra Alzensoy that were in SESAME here. They were in the experimental station. So this is the old design of the experimental station. Now we have a completely new one. These are PhD students from Bilkent University. So nowadays, I mean, everybody now is thinking that the fuel or the energy is totally depending on or not totally, but mainly depending on the fossil fuels like oil, gas, and natural gas, and coal, and so on. The other thing is that these resources are tending to be terminated, or to at a given time there will be no petrol or no gas, because we are just using them, and they are not easily renewable. So people are going to looking really for renewable energies. And I think most of you, or some of you, are working on these kind of renewable energies. And so they wanted to get biodiesel by changing the glycerin. So they started really doing some XPS to look at, and yeah, what they were using this AZT. AZT stands for aluminum oxide, zirconium oxide, and titanium oxide as a support for the catalysis for rhodium, nickel, and cobalt. And they wanted to see what is best for the as a catalyzer. So with rhodium, the starting is it's majorly the rhodium, the metallic rhodium, with a minor rhodium plus and rhodium 3 plus. And after 72 hours of after conversion, there is a slight decrease in the rhodium 3 plus. For the nickel, they start also for nickel 0, and we have some minor nickel oxides and nickel hydroxides. After 5 hours, we have a decrease in nickel hydroxides, but after 72 hours, the nickel hydroxide regenerated and came back. For the cobalt, we started from the major is cobalt oxide. But we have also some other cobalt oxidation states. After 72 hours, the cobalt completely or mainly converted into cobalt 304, which is a mixture between cobalt 2 plus and cobalt 3 plus. And then they did some IR. So this is not from my side, but anyway, they have seen some carbon oxide, the presence of carbon oxide with the catalysis. Sorry, it went by itself, but anyway, I don't have much to say here. And then after, when they just characterize their samples, they want to know a little bit more with the XANES about oxidation states of nickel, cobalt, and rhodium. They came with the samples to the beamline, and here we show the cobalt and the nickel. For the cobalt, we start with the 7 but mainly cobalt, metallic cobalt. Then it was with a slight number or small amount of copper 2+, copper 3+, and after conversion or after 5 hours, we got a decrease in the cobalt metal and an increase in the 2 other states, oxidation states. Yeah, that was exactly the same, but for the nickel, it was completely different. And the nickel, I don't know, so the glacial and the copper oxide dioxide or conversion decreased in rhodium, decreased in nickel, and in cobalt it was quite higher. So the conversion was quite higher with the cobalt. And then they went into the conclusion based on not only on the XAFS or the XANS, but also on what they have done with the XPS and also the infrared FTIR, that rhodium and nickel are, I don't know if, I don't remember exactly. So, but anyway, so this is about the cobalt was the worst stable, the most the less converged and the less stable one, but rhodium and nickel were the more stable and the more conversion systems. Another example, it's about material, about energy storage. So this is also another group from Turkey, where they look at the lithium batteries, lithium manganese oxide cathode material, where they we just substitute the boron atom into the lithium, into the manganese by ratio 1 - X to X or 1 - X. It's just a substitution atom to atom, and here we can see when we increase when we increase the number of substituting boron atoms, we have a decrease in the white line and also in a decrease in the number of surrounding atoms. And I think yeah. So it was now from this project that the manganese atom they formed a cubic. There is a split in the system where we have a formation of lithium manganese oxide with where they present good electrochemical properties. And then the substitution had into having other species like lithium 2 manganese oxide 3 and the lithium boron oxide, and also lithium manganese oxide, another form, and this increased the intercalation and the electrochemical properties. So the conclusion, I think, for this one is with the substitution of boron atoms in the manganese coordinated in the manganese sites acts as landmark for the parent oxides by forming lithium boron oxide crystals. So I think, yeah, this is the end. Before, I think we have already 40. Yeah, we are in time. Before ending, I have to acknowledge first all the SESAME staff for their support, and also it was beamline for training, so they had to learn a lot from this beamline. Then also I have to thank the Helmholtz-Zentrum Dresden-Rosendorf for the donation of the optics from the old Robel or the Robel 1 at the SRF. Also the INFN for the 64 element detector, Diamond for the new DCM, and also all Argonne National Lab, and Brazilian also synchrotron. So I think with this one I'm done. Thank you very much. And if you have questions, you can also visit the website of the Beamline. For more questions, also you can contact me with the email, and I will be more than happy to talk more about the Beamline or help into developing new collaboration research. Or if you have a toroidal mirror lying around and it can fit into our Beamlines, we will be also happy. Thank you very much.
Okay, thanks. That was wonderful. There was a question in the chat and from Jerry, who had to then leave. Asking which technical measurements are most requested by the users, like fluorescence or XRF or bulk XAFS. What are the main technical requests?
Yeah, it's more generally it's more XRF that we do, but also for the material science groups, they generally combine between transmission and the fluorescence mode. So we do both fluorescence and mode and transmission, but more fluorescence is demanded because of the fact that we have a lot of proposals about archaeology, and archaeological people, they don't know about their samples. They have to start with XRF first and then going from XRF to doing XAFS in the XRF mode also on some elements.
Right. So I was going to ask a follow-up question to that, not technical, but scientific. What are the fields that are most in demand? I think you mentioned archaeology, and you showed other examples. Is that the right proportion or the current proportion of requests? Is it heavily archaeology and cultural heritage, or is it as much, or what's the breakdown between the cultural heritage?
Things that the region here is full of archaeological sites, and there are many groups and many European institutions in the Middle East. They were first in Syria. Now most of them moved to Jordan, like the German archaeological institution, the French one, and all of them they really good, and they want to use the facility to understand the nature of the pigments and everything. So we also have from Turkey, we have shipwork from the Ottoman Empire. They want to look at the they use some material for the preservation, and it seems that I think there was a problem in this one. Also, there were many applications from archaeological. The region itself is an archaeological place. But also we have other applications in material science, also geology. We have chemistry also. We have most of the applications known.
Okay, thanks. Matthew Marcus, I think you had a question.
Yeah, among the techniques you didn't mention was total electron yield, which I find can be very useful. So do you offer that?
No, we didn't think about. I mean, just we are working at higher energies, and then I think just fluorescence is good.
Yeah, the TEY with the helium box works pretty well for things like standards where you want to avoid overabsorption.
Yeah, but I mean, we are limited in the energy by the monochromator itself. We cannot go lower than 4.7 kilotron.
That's fine. You can still do TEY at higher energies.
Yeah, I don't know.
It works pretty well.
I didn't think about it, so maybe I will think about it. I'll see if we can use it. Thank you.
Great. Any other questions, or I'll ask while we're waiting for other questions, I'll ask another one. So you talked about technical and scientific. Are there what I'm going to say political or regional or national breakdowns for who's using this source and who gets access to it? So is it, you showed examples from Turkey and from Iran. Is it, is that allocation of beam time include a political equation?
Yeah, in order to be really not to be in such thing, I mean, we have all, it's like all the other synchrotrons, all the proposals are accepted based on the scientific merit. So we have a community from the worldwide. I mean, we have from everywhere, from the USA. Also, we have members in the committee, and they evaluate the proposals based on scientific merit. The other hand, we have the in-house research and also the other director beam time, and that can be used for some political issues. So,
sure. If there's not another question, I'm going to ask. So it seems like you also are in a position of both sort of needing, but also having a great opportunity to do a lot of teaching and outreach. Both, science for peace, but teaching for what these techniques can do. And do you feel like you have enough resources and tools to do that, and enough, time to do the teaching aspects?
Yeah, I didn't get the point. Sorry, but my sound here in my computer is not good. If I understand that you are saying that if there is a possibility to teaching the technique in the region, right?
Yes, yes.
Yeah. There is, I mean, I'm giving lectures for the universities here in Jordan, but the thing is that we are oversubscribed. We are just 2 persons on the beamline, and we are the scientists, engineers, and technicians.
Yeah.
So it's quite really quite difficult, since I mean at SESAME we are just 60 employees, including administration, technical sector, and scientific sector. So you can imagine how what's the load that we have on our shoulders.
Sure. Yeah, of course. Looks like maybe Bruce has a question or a comment or a.
Yeah, Bruce is in the proposal review committee, right?
Yeah, I want to address the thing you just asked, Matt. Judging by the increase in the quality of the proposals, I would say that these guys are doing a really outstanding job fostering their community and reaching out to their community. The quality of the proposals has increased over the last several years very noticeably.
Okay, great.
Yeah, thank you, Bruce.
Awesome.
Hi, by the way.
Okay, are there any other questions or comments on this wonderful presentation? I hope you can find the optics you need, either the resources for them or the donations.
No, yeah, unfortunately we don't have the resources, but we are looking. We keep looking. We never gave up.
Yeah.
Okay.
Great. Okay, well, if there aren't any more questions, I'll stop the recording, but we can continue in private discussions.